tell us about Tic Tac Types.
All right, hello. I am Sean, and I'm talking about Tic Tac Types. Realistically, this is less of a talk about, crazy out of this world type features as some people talk about, and more how types can help more everyday programmers, and hopefully there's something to be seen in that. And I skip over a lot of the gritty details because obviously you guys aren't going to care about that very much, but hopefully there's still something to be seen here. And really, the Tic-Tac-Toe example comes into play because it contains a lot of elements of not only just different games, but different examples. So some of the stuff here is applied to dependent neural nets and stuff like that, and hopefully that means it's a good stepping stone for stuff like that. Okay, so the rules are pretty important if we're going to be being precise about things. So X goes first, but there are two players, X and O, on a 3x3 grid, and then the pieces go like that. So X goes, O goes, blah, blah, blah. 3 in a row wins. I think most people know the game, but just to be precise. Yeah, it's really that. And so how can we represent this? I don't need to convince you guys that strings are bad, so I'll just keep going. We introduce X and O, and that's going to help out. And then we start to see things that look a bit more like a grid, but a list of pieces doesn't really give us any structure, so that's not ideal. And a list of pieces, it could just be any size, potentially infinite, and that's going to be a bit annoying. And specifically, it could be like 5x4 or something, which isn't even a grid. So a tuple lets us be extremely rigid, 3x3, but a good thing about dependent types is allowing you to generalize. And say we wanted to play a 4x4 game, we don't get that at all, so let's do what we all know is coming, the vector. We know what this is. It just lets us use list syntax, which is nice. We get lots of interface definitions, very nice. This is a data type composition of vectors, so that's the base board type for the rest of this, and it just takes a number, and then you have a grid, and that's great because that's exactly what we want with a generalized sort of tic-tac-toe game. And so tic-tac-terrific, board 3, maybe piece. It's always going to be a grid 3x3, and no other sizes allowed. Very easy to switch to 4x4. That's exactly what we wanted. So I'll just look at some small aspects of game logic because it's not that interesting, but here's a neat little bit. We can define, instead of doing a Boolean type for whether you've won or not, we can define a much more specific type to tic-tac-toe. So the 3 is from when you get 3 in a row. The piece is the player who's won, and you can only construct has won when that nat that you're constructing with is 3. That's not enforced here, but it will be later on. So this type is really what's doing the work. So it takes a piece, it takes the board, and this most pieces function that's being called will work out what the most pieces are on any line, on all the lines. And so really this type is nice because it ensures soundness. It's not possible to define the one function in a way where you let someone win when they haven't won, assuming most pieces is correct. So the definition follows quite easily from that. This only problem with this is that 3 doesn't generalize to 4x4 and stuff. So really it's 3 in a row on 4x4 grids as well. It wouldn't be too hard to make that more general, but it just makes the code a bit nicer. So making moves, this is also quite simple. I'm mostly just showing this because it comes up again a bit later. So you have a move, a piece and a board, and then inside an error monad, we also have a piece and a board again, which is just, if everything's gone through correctly, the piece is swapped to X or O, and the board has the new piece applied to it. So that's all that's happening here. So assert nothing is saying, so 1 was returning just has 1 or nothing. So 1 will return nothing if the game hasn't been won and we can proceed. If it has been won, we error with game 1. And then the same if the position's taken, that's just the lens hiding behind there. So get move board gives you position taken, and then if that's nothing, because the pieces are either nothing or just something. So once again, you can do that. And then if that's all gone through, swap player, apply the piece to the board. Easy enough. So this is good, and it is tic-tac-toe and it works, but is it good enough? The answer is probably yes, but we'll take it a bit further anyway and see where it goes. So the idea here is to basically just shove everything into a type well, a data type, and play tic-tac-toe on the type level. And this ensures that any game that you see as a data structure that you're handed has been played validly and built validly. And it means that this make-move constructor needs to now become a constructor for a data type. And that looks like, okay, so firstly, we have to have the start constructor, which is just, you see on the type it says pure nothing. That's just going to be a blank board of the size that you specify with that n there. And then the x is just saying x goes first, which is another rule, yeah. So the turn, it takes a move and a board. That will be stored just like a normal data type stores things. And then it does the exact same checks again, but this time they're written as proofs. And that just means that it's not possible to construct something that doesn't satisfy these. And okay, so then it applies the piece again, swaps the player. So it's basically the same thing. And so this is the example that we had at the start, and I'm going to turn this into an example for Tic-Tac-Titanium. So I play X, you play O, then I play X in the middle, you play O on the top right there, I play X out the bottom, I've won, except O's gone again. So actually, the example from earlier was invalid, as this clearly demonstrates. And that's just something that a compiler catches really easily, but is not so obvious to us. But you just take moves, and if you try and do another move, it's not going to compile. And that's nice to have, but realistically, it's a limited benefit. We'll probably find where we were before, given that it still just relies on these get and won functions, and it's a pretty considerable increase in implementation time, at least for me. So let's take the lesson learned that this is perhaps too far and apply it to a slightly more complex example, which here is going to be a recursive version of tic-tac-toe, which looks something like that. So you start with an empty board, which I didn't put a picture of, but oh well. It's essentially everything goes down to the same level. So tic-tac-toe boards are branches, pieces are leaves, and so there would be a board in each space in this example if this is a depth 2 game. And pieces are only played on the bottom level, and you win positions by winning subgames, and it moves up. And it can cascade, and then if say, an X went right about here, they would win that one, then you would get a line here, they would win that one, this whole thing would become X, and they've won the game. And that can continue on down forever, but you don't want to play that long. So a tree captures this nicely, pretty clearly, I think. Leaves of pieces, branches of boards. Win conditions can be applied recursively quite nicely. Moves can be placed in other ways. Really, this is just free hiding there. So the board is actually the signature functor, and the leaves are still the pieces, and everything's pretty much the same. But this gives us some folding stuff for free, which is really what I'm after. But the depth of the tree could be unbalanced. And as I said, we want everything to be balanced at the bottom. So as the vector is to the list, the index-free monad is to the free. So let's just push this a little bit. You can see it's basically the same thing. Every type becomes a K to type, except A to free FA becomes AN to I free FAN. So it's just another parameter, essentially. And that's all that you really need to worry about, except that this syntax functor that we had here is now an indexed syntax functor. So the exact details of that aren't really that important, to be honest. But it just gives you an extra parameter on the type level, which is nice, because now our signature functor can access this value, mess about with it, and hopefully do what we want. So this lift operation is just going to take a board, the board that didn't care about any of this stuff before, and suddenly make it care about it, but in the stupidest way possible, so it's just the same board on any given parameter. And then the key thing to note is a tic-tac-toe on one level, n, is then promoted to another level, a higher level. So the tic-tac-toe game finalized will now count down into the tree. So this tic-tac-tree thing, tic-tac-tree 5 will have 5 levels, and that's exactly what we were after, so great. This is recursive win checking. Again, the details really aren't that important. The only real important thing is that I've just used the same one function from earlier, and it's cascading up using a catamorphism and some extra plumbing. And the final win check is just seeing, is the entire board just one piece, or is it still a board? And then you can say if the person's won. So conclusion time. Types are clearly powerful and they can do a lot, and really what I've been showing here is how you can gain specificity, which compilers love, without sacrificing generality, which is something that we as programmers enjoy because it means we have to write less code. Just don't do more than the compiler can handle or your own brain can handle, really, because it just starts to get difficult. But if you find the balance, then you can be rewarded with these quite quick to implement things that are also pretty high quality and are pretty robust because types give you that kind of safety. Okay, thank you for listening.
So we have some time for questions. I don't see any on the slide, but I have a couple.
Okay.
So my first thought was, we saw an excellent demonstration of Idris's power to autocomplete the more types you give it. You didn't use that anywhere in here or discuss that. So did you take advantage of that while writing any of these?
I did while writing the code a bit, yeah. One good example was you can just kind of, when creating a board, you can just kind of autocomplete and it will draw a tic-tac-toe board for you. And, well, there were other little examples, but you have to be quite careful to get that to work, I think. But when it works, it's quite nice.
And presumably in the Tic-Tac-Titanium, they will only generate correct boards when it does that.
Yes. Yeah.
Yeah.
I'm trying to formulate a question about the recursive one. You started off with the 3x3 board, which is a applicative structure, so that's like vectors.
Yeah.
Vector length 3 or vector length 3 or something. Then you went to index-free monads. I was expecting some kind of free applicative. Well, there's some applicative structure on these. These are perfect trees of a given, perfect
Yes.
binary trees of a given depth,
Well,
which is an applicative.
it depends what properties you're after, I suppose. I quite like the idea of this recursive win thing where so the level of the tree folds up and then it's reflected nicely. The exact kind of applicative nature is a bit harder to recreate, but there is the indexed applicative, which you can use. So I was just kind of following that line of thinking, I suppose. It's not quite, well, I mean, there are nice things about each approach, I suppose, but yeah. Okay.
Any questions?
Great.
Okay, I have one more.
Okay.
So as you were going through your examples, it seemed like the lesson here was almost intrinsically typed data structures are maybe too much. At least for this tic-tac-toe example, it seems like much too much machinery when you want an intrinsically correct representation
Yes.
in order to implement tic-tac-toe.
It really depends on your use case, of course, but I think with the kind of people I was aiming at when I was writing this, and also just in general, there becomes a lot of overhead, and it's just kind of a mess, and it's better to be avoided unless you really know that you need those sorts of benefits. Because there was that one benefit of knowing that it was correct.
So what you didn't talk about was the tooling support or the sort of additional meta-theoretic correctness guarantees you can sort of inherit from the system when
Right.
you work with this sort of representation. Do you think that's sort of crucial in some applications and maybe missing here?
Yeah, well, it's definitely very important in a lot of applications. I think I was focusing on, well, when I was making it, I was looking to the theory and trying to kind of adapt it to things that are important, and that does show up a bit more in the paper. And I was just kind of ignoring it here and showing the highlights, I suppose. But there's, there's some more kind of, it kind of works from some theory that I found that kind of matches quite nicely to what I was trying to do. And so hopefully that kind of makes sense.